All right, greetings all. This is our beginning of our Shippensburg University General Chemistry YouTube channel. And more specifically, this is for Chemistry 125, which is a lab that goes along with Chemistry 121 chemical bonding. And I'm here today to start out the first installment of our YouTube channel. And we have a couple students that had general chemistry within the last year doing the recording of this, so they may chime in with some questions or suggestions as we go along. So in this first installment, what I'd like to do is to do review a few things. So at this point in the semester, you've checked in the lab, you've done the initial activity on significant figures and scientific notation, and you did the activity where you measured the density of lead using two methods: water displacement to calculate volume, and then assuming that the pieces of lead were cylinders and calculating the volume using the geometric formula. So there's some things that should be in pretty good place now before we move into a series of experiments that address some more complicated topics. So just before we get too far into this, what we have here is just a checklist of some basic stuff you should have in place before we even go anywhere. And if you have trouble with any of this stuff, make sure you go to the resource room, the CRC, go see your professor, get extra help. So you should be pretty good with sig figs and scientific notation at this point. Most of what we're doing in all the labs coming up are multiplication and division, not everything. So sig figs are pretty easy. You report your answer to the lowest number of sig figs, which is usually the number that's given to you, but we'll get there. You should also know how to calculate averages, standard deviations, percent errors. So standard deviation is precision, percent error is accuracy, so those are things you should know. You should understand how units work. You're putting units on every measurement. Every time you do a calculation, every measurement has a unit that comes along with it. And then you should be pretty good with taking one unit and converting it into another. Grams into pounds, liters into milliliters, all those things. I'm not reviewing any of that here, so these are basic skills. And then also lab notebook maintenance, which we're not going to talk about much here until we get to some complicated labs and we have to think about the data tables and how they're set up. Not necessarily this semester, that'll be crucial next semester when the experiments get a little more sophisticated, and keeping track of your data is very important. So that's sort of our basic skills. Okay, now next week, or whenever you watch this video, it doesn't really matter, I suppose, the next lab that we're doing is our first lab on stoichiometry. And that's really one of the big concepts in the first semester. Stoichiometry, as you know, is measuring matter and then doing calculations on matter. How much of a product should form in a reaction? How much of a reactant do you need to make a certain product? These are very practical questions, but to answer these requires quite a bit of prerequisite knowledge. So this is a checklist, okay? So nomenclature. If I give you a chemical formula, you should be able to write the name. If I give you the name, you should be able to write the chemical formula. So hopefully some things like that. I'm not going to go into all of these details, but you know, if we write something, I'm just going to make something up here, that if I write NaCl, well, first off, you know that that's an ionic compound because it's a metal and a non-metal, so that has its own set of rules. And you call that sodium chloride, something you've probably known since 3rd grade by seeing that, okay? Then, something else like CCl4, you might recognize that as a covalent molecule because it is nonmetals. Carbon and chlorine are both nonmetals. That has its own set of rules where you use the Greek prefixes. Carbon tetrachloride. So those are some things you should know by now, but now there's some information that you would need to know. So say I gave you something like, I don't know. Let's just do one in the other direction. Calcium chloride. Well, if you aren't thinking very much, you might just go CaCl and be done with it. But that's not right. Some other things you need to know. Also, this is ionic, metal, non-metal. But now you have to pay attention to the charges. And I don't know where you are yet. So here's just a generic periodic table. So maybe some of you have already done this. Group 1, when they're ions, they form +1 ions. Group 2, when they form ions, +2. Then we tend to jump to the other side of the periodic table. So group 15, which is the nitrogen group, tends to form -3. The oxygen group, also known as the chalcogens, form -2. The halogens form -1. So some things you need to know here. Calcium is +2 when it forms an ion. Chloride is -1 when it forms an ion. Therefore, the formula is CaCl2. So that's just a basic overview. There's other rules in there, using Roman numerals for transition metals, and some nuances to nomenclature. But you definitely need to know formula to name to formula for ionic and covalent. And for the next lab that you do, the empirical formula lab, it's ionic. That's the key. Because you're reacting magnesium, a metal, with the oxygen in the air, a nonmetal, and you're actually then forming magnesium oxide, an ionic compound. So that's really important. Some other things that are important to know as we go on are some basic ideas associated with the mole. You did the Avogadro's number lab where you use stearic acid, a saturated fat basically, to calculate an approximation of Avogadro's number, and if you got anywhere in the ballpark of 6.022 times 10 to the 23rd particles per mole, in your case, it wasn't just particles, it was molecules of stearic acid per mole. If we used lead to do the experiment, it would be atoms of lead per mole, so particles is just a generic placeholder, if you will. So that's fine. You generated Avogadro's number, and that's how many particles you have in a mole. And for us, it's either atoms per mole or molecules per mole. That's really what we're dealing with in chemistry. The other concept is molar mass, abbreviated with a uppercase script cursive M. And there's really two flavors there you want to know. The easy one is periodic table directly. So the molar mass of lead, for instance, that's easy. That's an atom. You just look it up. If I can find it. Oh yeah, there it is. 207.2. You don't stop there, of course. You don't just write 207.2. That would be grams of lead for every mole of lead. Grams per mole. All right? Well, what's another example? So that's sometimes called atomic mass. Sometimes professors refer to that as the atomic weight. Mass and weight, for most chemists, are interchangeable. Physicists, they tend to worry more about that than we do. But what if you need something a little bit bigger than this? Stearic acid, for instance, is, I have to look up that formula. Stearic acid from your Avogadro's number lab, the chemical formula is C18H36O2. And I think you can do the math, you should do the math, add up 18 carbons, 18 hydrogens, and 2 oxygens. Just do that math, I'm assuming you can all do that, and see what you get. And then just because it's a big molecule, it's always a good idea to go compare it to either a Google search. Imagine if you just type it into Wikipedia, stearic acid has a page. Why? I have no idea. But it does, and you can just find that out. The formal name of stearic acid is octadecanoic acid. That's because octadecanoic means 18 carbons. When you take organic chemistry, that'll make more sense. And I'm just looking up the number here. 284.48. And that's grams of stearic acid per mole of stearic acid, just using SA as an abbreviation. I just don't feel like writing all that out. Okay, that's fine. So atomic mass, molecular mass, weight, mass, sometimes synonymous, and that's fine. So those are things that should be in place. For now, all you have to do is treat Avogadro's number and molar mass as conversion factors. If you think of those as conversion factors, okay, do I write the 207.2 in the numerator, where there's grams, or do I need 207.2 in the denominator, grams in the denominator? Think of these as conversion factors. In fact, some students like to do it this way. 207.2 grams of lead equals 1 mole of lead. If you want to do it that way and think of it as a true conversion factor, that's fine. Hopefully you get sophisticated enough to realize grams per mole is it's the same thing. Whatever it takes for you to understand this. All right. And balancing chemical equations. Students that have had chemistry before, ever, even middle school physical science, you had to balance chemical equations. So, a couple things there. There's really only one general rule for balancing chemical equations. You can only change the coefficients. What is that? That's the number in front of the chemical formulas. You do not change the chemical formulas themselves. I don't think that's really ever been a problem. So what I'd like to do, and you can either stop the video, is show you some examples of chemical equations using the introduction to your empirical formula lab. So if you have your lab manual handy, okay, find the introduction to your empirical formula lab. There's actually 3 chemical reactions that are relevant for this lab. Now the chemical equations for those 3 chemical reactions are nowhere to be found. Okay, they are not written for you explicitly. But if you're clever, which you are, okay, you can read through this information and figure out the chemical equation from the information given, and then we'll balance it. So that when you walk into lab next week, you know what the 3 chemical equations are, and you're ready to do the calculations. And that's where we'll actually end this video and start the next one. So take a minute, look at the introduction to that lab, and I just need to erase this, so either pause the video or relax for a second. So I'm just going to read sections of that introduction. You can either pause it, read the whole thing yourself, see if you can figure it out yourself, stop the video, and then come back. That's fine. That's the nice thing about these. Okay, so these are, I guess I can label these for you. Chemical equations for empirical formula lab. Interestingly enough, I don't even think you need the chemical equations to do the lab itself, which is fine, depending on the pre-lab lecture that your professor gives you. So I'm just going to keep reading this. And about, I don't know, middle of the way through the second paragraph, it says, the formation reaction of magnesium oxide requires magnesium and oxygen as reactants. Okay, so we're told what the reactants are, and we're told that we're forming magnesium oxide. So how do we take that sentence and make it into a chemical equation? So it's magnesium and oxygen as the reactants. Magnesium is pretty easy. It's just an element. It's not diatomic. It doesn't have a special, it's not like sulfur where it's S8. It's just magnesium. And we're just going to give you a piece of magnesium metal. So it's a solid metal, and it reacts with oxygen, and that's something you just need to kind of know. The oxygen in the air is O2. That's about 20% of the air you're breathing. So it's just oxygen that's in the air. Okay? So those are the reactants. I think you know that already. Reactants are on the left side. We draw the arrow. That's yields, produces, more informally, makes, what have you. Now magnesium oxide, you have to think about that one a little bit. And actually by doing this, I'm kind of giving the answer away to the lab, but that's okay. Okay? Magnesium oxide. Metal, non-metal, magnesium's group 2, that's +2 when it's an ion. Oxygen is in group 16, so that's -2. Well, that should be pretty easy. It's just magnesium oxide. If you're not sure where I got that, look at the ionic charges, and it's just one of each. And you'll see this in lab. This will be a solid. And that's it. There are no other, there's nothing else going on in this reaction. This is the first chemical equation that you're going to need. We have 3 of them. It's pretty traditional in chemistry to number the chemical equations, so we'll call that equation 1. And we have to balance this. Students have different ways of doing this. I'm not going to spend too much time on this. I just kind of start with the first element, and I usually balance hydrogens and oxygens last. So magnesium's easy. There's 1 there and 1 there because there's a subscript assumed to be 1, so that's fine. 2 oxygen atoms. There's only 1 oxygen atom. Again, all you can do is change the coefficients. I have no choice but to put a 2 there. I would never put the 2 in the middle. I don't see that very often, but occasionally I do. And the 2 then distributes to the magnesium, it distributes to the oxygen. Of course, now I just screwed up the magnesium, but that's fine. I just simply go back and correct it there. Okay. So you keep reading, and let's see. Further down in the paragraph, it says, since air consists of many reactive substances in addition to oxygen, the magnesium, the piece of metal that you start out with, I just lost my place. Okay. Oh, yeah. May react to form other compounds which would interfere with the chemist obtaining an accurate result. That means obtaining just magnesium oxide. So here's an example. For example, magnesium nitride may be formed. Well, so we have another. So it gives it away. Okay, magnesium nitride. So magnesium may be formed. That's the product. Well, so it's magnesium and nitrogen. So it's magnesium with a +2. Nitrogen has a -3. So I'm going to let you figure this out yourselves. And that's also a solid. So you can figure that one out yourselves. Some people do that crisscross method. The charge on one becomes the subscript on the other one, or whatever. I see that in a lot of high school books. That's fine. Well, what are the reactants then? Well, it's still magnesium. And nitrogen in the air is just this, N2. And I think we're done. So that's the second reaction. Keep reading. Keep reading. In this lab, the whole point is to analyze magnesium oxide. This is a byproduct. So it's a secondary reaction. It doesn't happen as much as this first one, but we get some byproduct that we don't want. Magnesium nitride. So what we do is we actually convert magnesium nitride back to magnesium oxide, and that's where we have to read, how do we do that? It's pretty simple. We just add water. It's kind of interesting. I never did that part of this experiment when I taught before. Yeah, here we go. Keep reading. The last sentence of the last big paragraph. However, the nitride can be removed by reacting the product, which that means this product. So we have a third chemical equation. So we take the magnesium nitride, solid, we let things cool down. You'll see that in the lab. Things are very hot in this lab. Nitride can be removed by reacting the product with water. So just going to drip some water in there. That's an L for liquid water. To produce, well, I told you what we're trying to produce is, we're trying to get this back, so that's one of the products. That wouldn't work though, we need others. That wouldn't work like this, we have to add something else. So reading the clues. Oh, it produces ammonia gas. Now ammonia is one of those you probably just want to know. And you'll actually smell the ammonia if you're careful in the lab. You'll add it, you'll heat it, and you'll smell a little bit of ammonia come out of your reaction mixture. And I think that's it. We at least have magnesium, nitrogen, hydrogen, and oxygen atoms on both sides, so we're not missing any atoms. And let's go ahead and try to balance this. I'm not going to do that. You can do that one. You can balance that one on your own. So when you walk in the lab, you'll have all three of these chemical equations ready to go. You actually don't need these because the point of the lab will be actually to make physical measurements on the magnesium. When I say physical measurements, actually record its mass. Do the chemical equation, figure out how much magnesium oxide forms after you go through all of this. And then you use that information to calculate the empirical formula. But I think that's enough for one video. That's what we'll talk about a little bit the next video, and then get into more stoichiometry where you calculate how much mass should form. So we'll look at empirical formula briefly. It's a pretty easy experiment, but then I'll also introduce how do you calculate how much magnesium, when you have a specific amount of magnesium, how much of the MgO should form. And that's called theoretical yield. That'll be the next video. Thank you.